Hey y'all, this is a long one because this is a combined section. So I'm going to break this one into two videos. We're going to start out with lecture 19, and this is from section, ideas from section 5.1 and 5.2. I don't really like the way they split them, so I kind of do it all together. And we're going to be talking about max and min. So one of the things that our goal was to describe the behavior of functions with calculus. And so one of the things we want to be able to describe about our functions is where we have local maximums and local minimums. So I'm going to start by drawing you a little picture here. So we want to start with a coordinate plane. And I'm doing my best here, so enjoy my sketching. I'm going to mark 1 and 3 and 5. And, we got some other points out here. And I'm also going to worry about -3 and -5. And I'm totally making this up as I go, guys. And then I'm going to draw a function here. Okay, so my function is going to be somewhere up here at 1. It is going to cross at 3. It will be somewhere down here at 5. It is going to cross somewhere like here. In particular, I'm going to have a point here. And let's see, one way down here and then one up here. So when I connect these dots, I'm going to do so in this way. All right, not my best work, but there we go. In fact, I'm going to fix this down here because I'm a perfectionist and I don't like it. There we go. Okay, so here's what we want to do. We want to be able to talk about the behavior of this function. So for some things I want to point out, here is what I would call a local minimum, a local min. And that's because compared to the things around it, it's the smallest thing. It's the smallest one in that vicinity. That means that this one over here is also a local min. And correspondingly, this one up here would then be a local max. Okay. And what I want to do first is I want to talk about the behavior of this function as we move from left to right. So whether it's increasing or decreasing. And I want to correlate to that to what we know about calculus, and that's to think about the slope of the tangent line. So the first thing I want to do is I'm going to highlight where do we think, or where would you say that this function is decreasing, or let's start with increasing. Where is this function increasing? This function is increasing from here all the way up as we move left to right till you hit there, and then it starts dropping again. And from our low point here, we're going increasing as we go right to left. Sorry, left to right. So on those two intervals, we are decreasing. And I didn't leave myself a lot of room, so I'm going to go over here to the side and jot some things down. So we are increasing on the intervals from, and these are x values, -5 to 1. So -5 to 1. And we can't increase at the maxes and mins because you're not going up at that particular point. So we don't use endpoints here, or we don't use brackets to close in our endpoints. And then also from 5 on to infinity, it's increasing. And then it's decreasing on the other intervals. So if we're going left to right, we're going down, 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 down to the bottom. And over here, we're starting at the top and going down, 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 down to the bottom. So it is also decreasing on those two intervals. And that's from -infinity all the way on the left up until you hit -5, right? And then it started increasing again. And then we start decreasing again at 1 and we stop at +5. So those are my intervals for increasing and decreasing, okay? Now it's doing neither at those particular points where I have my local maxes and mins. So there, and there, I have where it's changing, right? That's the changing points. So it's doing neither on the points x equals -5, 1, and +5. And what we want to do is we want to correlate this to the slope of the tangent line, right? So let's look at the slope of the tangent line. And so that's what we're going to do. So if we think about our graph where it's decreasing, so where it's green, I'm going to draw in the slope of the tangent line. So the slope of the tangent line would be like this, and just at various points along this green curve. So there, something like that, right? And then over here, my tangent line would be here, 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 right? And what do you notice about all of the red arrows? You notice that they're pointing down, right? And so that means where it's decreasing, the slope is negative, right? It's going down. And where I have my blue curve, if I look at the slope of the tangent line here, as I go from left to right, notice what's happening. They're all pointing up. That one actually probably goes on this side. All right, they're all pointing up. And so what we know then, where it's increasing, we know that the slope is positive. Let me just switch this because you can't read that. All right. And then what do we know about our slope at these points? Well, what we can say is, guess what? The slope here is 0. Slope of the tangent line at those points is 0. So the slope is equal to 0. So that's what's happening here, okay? So where it's increasing, where slope is positive, where it's decreasing, our slope is, let me fix that, sorry friends. This should say negative, right? And so that's what we get. So we can go down here and make a couple of statements. So statement number 1 says, if the first derivative is positive on an interval, then the graph of the function is increasing. So those things are related. It's not a fluke. They are tied together. If your first derivative is positive, then the graph is going to be increasing. If your first derivative is negative, then your graph of your function is going to be decreasing. Okay, kind of makes sense. And if the first derivative is equal to 0, at a point, and then that point might be, and we're going to put in local max or a local min here. Notice, and I'm going to highlight it, the word might be, okay? In our case, we could see the local min, and then we show that it had 0 slope. I'm going to be able to say, this is the opposite direction, right? It's saying, well, if the slope is 0, do we have a local max or min? And the question is maybe, okay? So one of the ways that we want to go about trying to find that local max and min is being able to start with the critical point. So critical points are where there are breaks in the graph or natural places in the graph where we're going to divide things up. So our critical points up here is going to be when our graph changes from increasing to decreasing. So these are going to be my critical points, right? And that's when the derivative is equal to 0 because my slope is 0, right? Slope is the slope of the tangent line is also our derivative. So for a critical point, x equals c of a function is where the derivative is 0, but we're also going to throw in this other condition. So being 0 is what we saw up above. It's also where this is undefined because oftentimes that creates holes or asymptotes or some points that do weird things. And we want to be able to break up our graph at these important points. So that's why we call them critical points. So if I was going to find the critical point for this example, for example 1, I'm going to do exactly what's here. I'm going to try to find the points where the derivative is equal to 0. So critical points, which I'm going to call CPs, we take derivative and set equal to 0. Okay, and then solve for x. And I spelled it wrong. So that's what we want to do. In this case, our first derivative, f of x, is equal to negative 2x. I'm going to set that equal to 0, because that's what I'm trying to do here. If I divide both sides by negative 2, I get that x is equal to 0. Okay, and that's my critical point. So my critical point here is x equals 0. So that's all that's going to work here. We're going to take derivatives and try setting equal to 0. Key things you're going to be doing here often, factoring, going to be important, right? When I push the, oh, here's how we simplify our derivatives, that's going to be an important aspect here. Now, why is this important? So what we want to do is once we've found our critical points, how do we know which of those critical points are a local max, a local min, or maybe it's neither of those things? Okay, well, we have two ways to do it, and the first is called the first derivative test. Notice up here that a local min is always at the bottom, which means your function has to decrease to get to the bottom, and then it increases. And then our max is always at the top, so it must have been coming from a graph that was increasing up to the top, and then it changes to be decreasing. So we can look at the change on both sides of our critical point and determine whether it's a local max, local min, or neither. So that's what we're going to do in the first derivative test, and it goes something like this. The first derivative test, first of all, it uses the first derivative to determine whether a critical point is a local max, local min, or neither. Okay, so that's the objective. Here's how you do it. So the first thing you're going to do, if you're going to test a critical point, you've got to find them first. So step 1 is to find your critical point or points. Now, the next thing that we want to do is we want to figure out where this function exists on the real line. So we want to identify the domain. And then you're going to break up your domain at your critical points to create intervals, right? So that I can, just like I did up above, I broke my graph into sections between -5 and 1 and 1 and 5. And then we're going to choose a test point in that interval, right? It's anywhere in between there. We can pick a number anywhere in between, and we're going to test it in the first derivative. And then I know that if the first derivative is positive, then it's increasing. If the first derivative is negative, it's decreasing. And I can use the relationships to determine whether the point is a local max, a local min, or neither. So here's how that would look. So let's go back to that same function. And first thing we did, which we did in the last step, was to say, okay, the derivative here was -2x. We set it equal to 0. We divided through by -2 and got our critical point of x equals 0. Now I want to test that using the first derivative test. So the first thing, next step after my critical point, is to identify the domain. Okay, this is a polynomial, right? I'm back to this function right here. This is a polynomial function, and so its domain is all real numbers. So we're going from -infinity to infinity. And then the next step is to break that up at my critical points. So if I think about the number line from -infinity to infinity, and I think about breaking it at 0. What that's going to do, I'm going to put 0 in the middle, and I'm going to break my interval there. So I'm going to go from -infinity to 0, stop there, jump over 0, and then go from 0 all the way to infinity. Okay, so that's how I'm creating my intervals. Then I need to choose test points. So I need some number that's in those intervals. I try to pick as easy as I can. So I pick 0 when I can. I pick 1s and -1s when I can. So I'm going to choose -1 here and +1 over here. And then what you're going to do is you're going to test those test points in the first derivative. So in f prime of x. So my first derivative is this one right here. Well, not with the 0. This part. Right? So the first derivative is -2x. So if I plug a -1 in for that x, then -2 times -1 is a positive answer. Now, I don't even care what the number is here. I just need to know that that is positive, and that tells me that the function, if the first derivative is positive, then the function is increasing. I like using symbols here because it creates a visual for you. So from left to right, I'm going up. Now on the other side, I'm plugging in a 1. So if I plug in 1 for the x up in my highlighted function, then 1 times -2 is negative. So I'm going to have a negative answer, and it's going to decrease. And now I can use my picture to determine whether my 0, my x equals 0, is local max, local min, or neither. So if my function is going up and then going down, in between there, this must be a local max right here at the top. Right? If it were down and then up, I was going down to a min and then back up again. So if it's down up, then it's a min. And if they don't change, if they're both up or both down, then you get neither. So this tells us that there's a local max at x equals 0. Okay, so that's what it tells us. And that's how the first derivative test works. Okay, great. I'm going to end this video here. And then we'll come back and look at another one with concavity.